So today is going to be kind of a little bit of a filler day. So I made you guys struggle through the first couple of days, getting the technology up and running, getting something trained, talking about how we can improve upon those models and search for better models. And I in discussions with many of you, you are all asking really good questions around interpretability, which is a fairly hot topic in the field. And I think it is due some time. And then I went ahead and added some inspiration. So usually when you get these tutorials for beginners, you get the forest and you only do those MNIST, the canned stuff, and you come away from it, if you're like me, going, great, I can run the stuff that you wrote as long as I don't understand it, until you start asking questions and it all falls apart. So I kind of flipped on its head. You've been staring at trees, not knowing you were in a forest. It was kind of on purpose, and I want to give you a little bit of the forest. One question that I kind of, several people kind of were beating around the bush, was a forbidden question in neural networks. And that forbidden question is, why these weights? And no, you can't get around it by rephrasing it. We don't actually know why those weights are optimal. Just as if, I have some data and I do a 100th order polynomial, right? I can fit a lot of data with that, but I don't necessarily know why those coefficients were chosen or do the thing. On a scale of, 50 parameters, it might be easier to tell. GPT-4 has about 1 trillion free parameters. So it becomes impossible to know why those weights work. There are, this is several of the kind of machine learning techniques, not all of them, but in general, you have like linear regression, which I think everybody in this room has probably done at some point in their life, a couple points. Very interpretable, right? You understand how to optimize 2 parameters and you can plot it and it's very nice. If you have complex data with scatter, the higher you go in order polynomial, the more accurate you tend to be able to be, but the less you can interpret it. You have decision trees, random forests. Remember this one, I make a joke about it later, and I'd appreciate laughter. We have gradient boosting, and we've been living in this neural network land. And part of the reason I chose here, instead of trying to choose this, is this forces you to think about problems, or think about solutions to problems rather, in deeper ways, because it's not apparent. Usually they do a very good job, they're very accurate, but they are pretty opaque. So there are some methods that give you uncertainty out of the box. As an experimentalist, right? I can tell you a story. First year grad school, I just got top line results. We had a group meeting, I plotted it, took it to the group meeting, and after the group meeting, my advisor pulled me aside and said, never, ever, ever show a plot without error bars. And I was in a rush, I just produced it. Yeah, I'm sorry, I could get the errors on there, it's fine. But it's true. That was a very bad thing that I did. I will never forget it. So uncertainty is actually probably more valuable. And there are some methods that provide it out of the box, namely Gaussian process, which I'm going to talk a little bit about in a moment. Most methods, though, don't have uncertainty out of the box. And you have to do some detective work to try to estimate those uncertainties. So I stole this slide from myself. And what this is we have a drift chamber, which we learned actually a little bit about the basis earlier. And we have all these straw tubes filled with gas, and we have them at a high voltage. And PV equals RT. As the conditions change, our gain of the detector changes. So we've asked the question, can we dynamically control all the high voltages in order to produce stable gains? And I'm not going to go through all of this, but we were using a Gaussian process. And one of the reasons we settled on the Gaussian process is that it gave us uncertainty out of the box. So we could set an uncertainty threshold and produce these, what we called bubbles of certainty. And everything inside this surface, this complicated surface, the model was less, more than, what is it? If the standard deviation is less than 3%, so it had to be like 97% confident or more inside. But we can't guarantee that a storm doesn't roll through and push our pressure down. We might get outside of our bubble of certainty. And you have to start thinking what do you do with that information, right? Do you not control? Do you project to a place of certainty because it's close enough? Depends on your application, depends on what the detector expert is comfortable with. It depends on many factors, but as an experimentalist, we gravitated to this this Gaussian process as a method, not because it was the most accurate, but our detector expert allowed us to use it, which is important. In doing this, we also did feature importance. And when you're doing machine learning, this is very important. There is, you can Google spurious correlations if you're willing to kill a few minutes. And this website finds spurious correlations in the number of drowning deaths and the attendance of a Star Wars movie. And you can get decent correlations between things that are not correlated. And so one of the problems is the more dimensions you have, the more likely it is that one or more of those correlations will be spurious. The AI may find that spurious correlation and do the wrong thing. So often you kind of do the spaghetti trick, you just start throwing variables and then you ask the question, which variables did I give you that most correlated with your output? They were the most important for you. Then you can cut down from 1,000 variables to maybe a dozen, and then start asking questions about the relationship between those variables. Are they expected or are they not? Can also make your training faster. It gives you an idea of what the model might be doing. My favorite anecdote story is cancer detection, and they were taking the scans and saying there's cancer, there's not cancer. They got a model that was very accurate. And they started asking the question, how is it doing it? And it turns out that on the scans was the name of the hospital. And there was the best oncology hospital in the area, which is where all of the patients were sent by the GP when they suspected cancer. So if you didn't know anything about the human body or cancer, you could guess probably somebody who had a scan at this clinic was likely to have cancer, because the only reason they went to that clinic is because they probably had cancer. So when you take that information away, suddenly it becomes a much harder problem. I put some links dotted throughout here. Please pull down the new slides and view other methods. We use this, so this is just a snapshot. We had a bunch of variables in this control problem. And you can see that there are only really 3 that mattered, maybe 4. These don't matter, so why are we even giving it to the model? We're just asking for trouble, making it more inefficient. Back to images. I like going to images. I'm a very visual creature, as most of you are as well. And there was a method called TCAB, which I thought is really clever, really cool. And it's testing with concept activation vectors, which just provides, as a fancy way of saying, it provides a global description. So the canonical example is, how do you know that is a picture of a zebra? And the model basically looks at other reference images and says, because it looks striped and zigzagged, it doesn't look dotted. And starts giving you a global description of why it chose what it chose. And so this one, I based on this tutorial. It's modified. Do this one last. It downloads the data. It can take half an hour to download the right data. but I have hooks in there where you can add new concepts and see how your concept activation vectors change. And then the kind of that's this more important one, not more important. There's GradCam, which is actually a method of doing local reasoning. So what it basically does is it says what parts of the image most excited the layers. So you can see, you can pass your input through, and then you can do math, as you do, on a specific layer and look at the response of the layer to specific areas of the image. This is great for figuring out what the computer vision algorithm is actually looking at. It can be hard to interpret sometimes. So let's see if this will play. Oh, it might have to go, it's not playing. Because it shouldn't be black. It the PowerPoint, if you can play the PowerPoint, but I don't know if it, can you click on it again? Yeah, maybe left. Yeah, the turtle is playing. If you can load the PDF quickly, if that's too much, not too much work. I think I have a still image from it, and I can give a similar thing. Yeah. So yeah, if you go to tutorial 4, yeah, click that link, and then there should be a .pdf. Sorry about this. Quite naturally, technology, you know, it's been so good to us this week, but yes, that one. Yep.
Quick question.
Yep.
Can you remind us, like, when are we supposed to laugh?
Oh, you'll know. You'll know. Oh, I may have. I didn't even do the saved image. Okay, go back to the talk, and I will just describe. I know clicking on it's not doing anything.
Oh. It just says you need access.
Oh. Oh, I didn't do the thing right. Okay. I'll just describe it in words. Yeah, don't worry about it. We'll just go to the talk. I will get that fixed. So if you look later, you should have access to it. You can see the video. But I have a project called Hydra, which uses computer vision to monitor detector performance and data quality. And it's a little like what I call a security camera view of each plot that it's looking at with what it thinks about the plot. And it uses GradCam to overlay. So it says there's a problem. And it says more than that. It says there's a problem here. And it shows you with a heat map where it's looking. So you can go, oh yeah, there's a bad pixel or a strip is out or whatever the problem happens to be. But if you look at the video, the parts of it are really, really hard to interpret. And we can discuss that if you like. But this leads me to attacks, which I find disturbingly hilarious. If it's a black box and you begin probing how it's doing what it's doing, and you understand the model as well as the data, you can do up to and including single pixel attacks. This is a turtle, right? Everybody agrees that's a turtle? Yes, okay. ImageNet is classifying this 3D printed turtle, and it believes strongly that it is a rifle. I give you turtle gun. So they, as you turn it and the AI watches, it actually changes which type of weapon it is. It's still a turtle though. Which actually I find very helpful when I have a model to probe for weaknesses. So I'm going to use this model for data quality monitoring. How easy is it to fool? Because depending on how easy it is to fool, I might not trust the model as much. There is some evidence lately that it's tied not necessarily to the model, but to the underlying data. My gut says it's probably a little bit of both. In other words, if you heavily bias your data set, fire trucks are red, right? Except for the places they're not. So it'd be easy to fool an AI into mislabeling the fire truck if it's green, that lime green, yellow, I think they use in Australia. We know it's a fire truck. Model had data only on red fire trucks. That's a problem with the data. This is another example. That sign says stop, right? Right, yes. I stole this from an article, but putting these little strips of tape, not even completely covering the word stop. It tricked the computer vision system for a self-driving car into thinking it was 45 miles an hour. Okay, awesome. So this kind of gets around this idea of how critical is your process and how much trust do you have in using it? That, this could kill someone. Turtle gun might get somebody erroneously arrested. The Hydra is just like wrong. The ship crew is not doing anything. But those various levels, you got to think about your application. How critical? How could things go wrong? You'd prefer not to have a model that drives into a wall when it sees that. And so today we're going to play around with some of these methods. And I just kind of basically take a look at your model. Pick one. Pick one. Can you trick it? Can you take that input data, add data to that matrix? And can you fool it? How badly can you fool it? How much does it take? Those are interesting questions. So now I'm going to do what I should have done first now. Okay. So we, I feel like we probably have not seen the forest for the trees. And I did this on purpose. We'll see how it works out. I made AI get another image, if you'll notice. Eyes for ears. I don't know why it does that so much with robots. So we're going to take a few minutes here, and I want to zoom out of this forest a little bit and give you a little bit of some of the other methods as inspiration. This maybe one will resonate with you. You can go off, do some research, and start applying some of these techniques to your own data and problems. So we've been here, sitting just in this little spoke, and you guys have been wandering through the random forest. This is the joke. See, you can't see the random forest for the trees. Okay, great. So what I want to do is take a look at some of these other branches. One kind of popular one for YouTube's makes great media fodder is reinforcement learning. It's generally useful to solve problems with competing objectives. It is state dependent. This state could be discrete. It could be continuous, but it basically involves having what's called an agent who has access to its game controller, to a set of controls. It can take some action, alter the state, and get rewarded or punished depending on what the state is. This self-driving is kind of like a reinforcement learning where you get points the longer you don't hit anything and follow the rules of the road. Other game AIs, another reinforcement learning method. So this one, can you make mistakes while learning? You don't want to teach a car to drive itself out on the road at first. You'll get a lot of destroyed cars and destruction. But if you can do simulation, you might be able to safely train it self-driving and then put it on the road when you're more confident. You're trying to learn this optimal policy. It's like a loss function. It's called policy. It's a loss function. And given the state, you want to perform the best action to maximize your reward. And through that state action relationship, you develop a policy that you're optimizing on. Unsupervised learning. This is generally used for data which can't be labeled or have no labels. Generally worse accuracy than supervised learning. Generally, not always, but generally. Because by providing it the target values or the labels, you're giving it more data to work with. It's comparative in nature. Things like feature extraction through encoders You can possibly use these techniques to jumpstart labeling. So I don't have labels. I do clustering. It looks like I have 3 clustering. I have 3 labels. I go to an expert and say, what would these 3 labels be? And they say A, B, and C. And then I label those A, B, and C. And now when I get new data, I can see which cluster it's a part of and just auto label it to A, B, or C. If it's not A, B, or C, then I may need to ask an expert. So this is how Netflix suggests things. It's really, this is what made Netflix a $1 billion company, is they use machine learning. This is what happens when you were talking about something and you swear Facebook was listening. It wasn't. You're just really easy to predict because people, turns out, are not nearly as unique as they would like to think they are. Sorry. The other part of this is compression. So you can kind of think in some ways an amplitude analysis, right? You have some data, and from that data we can extract a complex amplitude, a mass, a width. Maybe there's a couple states in there, so a couple mass, couple width, couple of complex amplitudes. And that becomes what's called a latent space, which represents the data. So you can take in the mass, the width, the amplitudes, do some math, and produce the spectrum. It's like that. Preferably for physics, we don't have the lossy bit. We don't allow us to lose the data, but sometimes, depending on what you're doing, might be okay. And so this is very close to line of best fit. So this is just a little graphic showing clustering in action. It basically uses features. These are the axes with distance measurements to determine which cluster it belongs to. You have to choose how many clusters. And if you pick too many, you get cluster sizes of 1. So usually what people do is they run with several different, 3 clusters, 4 clusters, and they take a look at what the clusters look like. And if you look at how this is doing, you might make an argument that there's like a cluster here, there's a cluster in the middle, and there's this cluster. It's not necessarily unique, and it's a little wobbly sometimes. And then we've been looking at supervised learning. These are expert-driven systems. You need the labels, which can be expensive to obtain. And then the fun fact is, all those CAPTCHAs, how they were starting out by letters, and then you did letters for like a year or 2, and now they're like, find the street signs. What you're doing, what you've been doing for years is training AI. So what they actually, most of those CAPTCHAs do is not let you in based on your answers. Let you in based on your mouse movements. So for example, if you ever get really good at them, right? And you're like, man, I found all the street signs. Why isn't it letting me in? You were so efficient, it doesn't think you're a human. But what you're doing is you're helping a self-driving vehicle recognize what a stoplight is or a stop sign. So take those really seriously, guys. It's really important. But it's what we've been doing for years. A lot of the other ones, like cancer detection, you have an oncologist circle an area on a scan that says this is cancerous, and then you try to get a machine to learn how to do that. You have to pay for the oncologist's time or to do the labeling, which can make it very expensive, and then you have privacy concerns and the like, which also make it costly. So in the tutorial 4, there's a few notebooks. Take your pick. If you think, what, I really would just like keep playing with the second, that's fine. So day 2, I'll be around answering questions. Have fun. Warning, TCAV can take a while. That might be a good dormant thing. Yeah, question.
I think the robots have eyes for ears because it's a hole in the head and it's a wave detector.
Yeah, exactly.
Not a particle detector.
yeah, probably. It's abstracted. Yeah, ears are like eyes for sound. Probably something like that. It's a very common problem with some of the earlier AI things is it's almost right. But eyes for ears. That's like